the independent particle shell model. So we have the following quantum mechanical problem. So we have a Hamiltonian, so the formulation is non-relativistic. So I do a non-relativistic approximation, and I consider the nucleons, so we consider the nucleons as elementary particle. I'm never going to talk about the structure of the nucleon itself, okay? And so then you have A nucleons. They have each of them have a kinetic energy, and then you have a two-body interaction, okay, which acts on the coordinates of two nucleons. You might have a three-body interaction which acts on the coordinates of three nucleons. And I've used here the notation psi. This is just one little clarification I have to give. This psi, right, it stands for the position vector, so which is associated with a certain particle k, the position vector of that particle, the spin, right, which is also a vector, possibly the isospin, and in fact, in principle, you could also here add the momentum associated with that particle, but this I will never consider. Right. So this psi is a sort of an ensemble of the variables associated with particle k. And I do this, well, I will try to do this consistently. Sometimes I just will write only the position vector, but in some cases I will specifically look at the properties of what is the influence of the spin variables of a nucleon and of the isospin variables of the nucleon. So the isospin, to remind you, I will discuss isospin in detail tomorrow, but just to remind you, so the convention is that you have isospin 1/2, that T is 1/2 for a nucleon, okay? And so you have two charge states, and the convention which is usually followed in nuclear physics is Tz, so the projection on the z-axis of isospin plus or minus 1/2, and so this is a neutron, and this is a proton. Okay, and so the idea is, instead of dealing separately with neutrons and protons, you say we'll deal with nucleons, and we will distinguish the two charge states of the nucleon by an isospin quantum number, and the isospin up corresponds to a neutron and the isospin down to a proton. Okay, the convention, this is the convention in nuclear physics actually. Particle physicists usually take the opposite convention. It doesn't matter as long as you stick to a consistent convention. Okay, you see here also that in principle you have a three-body interaction. You may have a three-body interaction because your nucleons are composite particles. Okay, and it can go on here. Okay, and so now the idea of the mean field of the independent, which is the basis of the independent particle shell model, is to say, well, I will have introduced here sort of a potential which is felt by one nucleon, right, nucleon K, and you can think of this as the interaction that it has with all the surrounding nucleons. Okay, and this is just added and subtracted. This is the mean field, and this is the residual interaction. Okay, and in the independent particle assumption, what do? You just say, well, let's in first approximation forget about the residual interaction, which is of course, that's a gross approximation, right? And let's take an independent particle. This was called by Rick IPM, I think, independent particle model. And so this is the independent particle Hamiltonian, which is a superposition of one-body operators. So this one should very well understand, even if you don't have three body interactions, but one body plus two body, this is a very hard problem to solve once that A is a reasonably large number of nucleons. Whereas if you have this problem where you have only one body terms, this is, well, I wouldn't say trivial, but it's very manageable. And so the reason is because you have here one A-body problem, and you have reduced it with this approximation, it's an approximation, you have reduced it to A one-body problems. And so you can solve the one-body problem separately and then put everything together. And how, yes?
May I ask a question? What is the meaning of dots in Hamiltonian?
Oh, so this, yes, this would be four-body, because there is no reason that the series ends, actually. There is no fundamental reason that there is no four-body interaction. So it can go on here. One hopes that the effect will get smaller and smaller. Here, the same thing. Well, here already I dropped the three-body term. And actually, in the lectures that I will give, I will always talk about just two-body interactions. But for instance, the algebraic techniques that I mentioned and that I will mention tomorrow, in principle, they can also deal with three-body interactions. There is no principal problem with that. Okay. So why is this easy, or let's say manageable? So you have now a Schrödinger equation for one particle, right? So you have this potential V1, this mean field potential which was introduced. It acts on one coordinate. Then you have a Schrödinger equation for one particle, and this is always solvable. I mean, in most cases you have a numerical solution, but it is manageable. Okay. And then if you have it for, so what you see here is states alpha. I will come later, so these are the quantum numbers that characterize, I'm assuming here that we are always dealing with discrete states, so this will be a discrete energy spectrum characterized by a set of quantum numbers, which I will specify or detail in a moment. Okay, and this is a solution. These are the wave functions of a one particle, so this is a one particle basis. And now the solution for many particles, at least a possible mathematical solution, is just a product wave function, right? So this is acting on one single nucleon. This is acting on A nucleons. Okay, so you have the A coordinates of the A nucleons, and it is just a product of the single particle wave functions in a set of quantum mechanical states. Okay, so the way you should think about this, just a little picture. So you have a potential. I will take here a harmonic oscillator, so this would be my V1, I assume. Right? So I have some levels in this potential, which I label by alpha 1, alpha 2, alpha 3, and so on. And so here I choose, in a way, arbitrarily any combination of those would be okay, right? And I form the product of that. This is a mathematical solution. It's not a correct solution. This is one, right? It's not the correct solution because, of course, we have nucleons, we have fermions, so we have to impose antisymmetry. And the antisymmetry is done by constructing a Slater determinant, so the famous Slater determinant, right? And I will follow the convention always, because symmetry or antisymmetry or non-antisymmetric wave functions are essential to what I will discuss here. If I have a non-antisymmetric wave function, so just a product here, this in general is non-antisymmetric. I will use the symbol, I guess this is phi. And so if it is an antisymmetric wave function, I will use the symbol psi. Yes, psi, I think, okay. And so now you see, if, look at the structure here, so you have the A particles, psi1 to psi A, okay. And these are the different columns, and then the different rows are the label associated with a certain quantum state alpha 1, the label associated with a certain quantum state alpha 2, and so on. And of course, if now two particles are sitting in the same quantum mechanical state, so if alpha 1 is alpha equal to alpha 2, then you have a determinant with two proportional rows, and then it vanishes. Okay, so this ensures that you have a wave function which satisfies the Pauli principle. Okay, and of course, well, this is an example, and I think, yeah, well, the energy of such a state, I haven't written it here, so, but it is just the sum of the single particle energies, right? K goes from no, it's not needed. I mean, it's just one to A, where the energies, I hope, yes, well, it's written here, sorry. It's written here. Okay, so this is the eigenvalue of the many body states. This works for the non-antisymmetric wave function. It's the same eigenvalue for the antisymmetrized wave function. Oh, yes, one comment. So I have a set of slides, and the slides always summarize what I will say. Okay. There is also available on the Talent webpage a set of my notes. Right. These are written notes, and there all the details can be seen. And so some of the derivations I don't have on slide, I will go and do them here on the whiteboard, especially the tricky ones. So the difficult ones I will go slow and try to explain how it goes. And these, I mean, I don't have the derivations on slides, but they can be found on the web page in my notes. Okay, so what is the interpretation of this guy now? So we now have the rule that we shouldn't put two particles in the same quantum state, so we have to put particles here. Of course, these levels can be degenerate, right? That was already explained by Rick. And if there are degeneracies associated, for instance, with magnetic substates, that means that we can put several particles at the same energy, but they should not occupy the same quantum mechanical state. So if you look at the complete list of the labels associated, right, the complete list, I will specify it later, but it will be the radial quantum number, it will be the orbital angular momentum, and the projection of the orbital angular momentum, the spin and the isospin. If you look at all the quantum numbers, then no two particles should be sitting in the same quantum mechanical state. So this is not allowed by the Pauli principle. And this is precisely obeyed by this later determinant. And this is a sort of a bit of a clumsy way of antisymmetrizing states. And so one of the goals of second quantization is that do this in a sort of more compact fashion. So this I will explain tomorrow. And this is by means of creation and annihilation operators. Okay. Now, I introduced here this one-body potential, so the mean field potential. And without saying how do you choose it, where does it come from? And so there is a procedure to find in the best possible mean field potential. And this is called Hartree-Fock. And this is the idea in one equation. How does it go? So you want to minimize, this is a minimization. Forget about this. This is just normalization, right? So you can assume that you have normalized wave functions, and this is 1. So you can forget, right? But you should always work if this works. If this can be forgotten if you work with normalized wave function. Okay. So the delta here, what does it mean? It's a variation of a function, right? And so you can show that the Schrödinger equation that I showed in the beginning, completely in the beginning, this one, right? This one. Right? If I take this Hamiltonian and I do this variational principle, right? So my Hamiltonian is fixed, but I will now vary the look at all possible wave functions, and I will minimize this with respect. Then this minimization problem is equivalent to the original Schrödinger equation. So that is nice, right? This one can show. And so now what the Hartree-Fock approximation is, well, to say, well, we do not take here a general wave function, we only take wave functions that are Slater determinants. Okay? So instead of doing a complete variation of all possible wave functions, we do a variation of wave functions of this type, right? Where we have here the single particle basis that comes out of the potential V1. And then we have a sort of an iterative procedure. How do we do it? We choose a certain potential, mean field potential. We solve it. This gives our basis, okay? And then we can calculate this this integral here. And I should stress the fact that here you take the full Hamiltonian, not the independent particle Hamiltonian, the full one, okay? You calculate this, then you do a variation of this potential. It changes a little bit the wave function, the single particle basis. You look and you see whether you have minimized the energies or not. Okay, so this is the Hartree-Fock procedure, and so it is trying to minimize the energy of a system, assuming that you have a Slater determinant. What is important is that these are solutions. These are the solutions of a single particle problem, okay, of an independent particle problem. So these have not, these are not the solutions of the full Hamiltonian, okay. But the minimization, in the minimization here, you can, without any problem, choose the full Hamiltonian. Okay, this is just something about Hartree-Fock approximation.
So,
yeah.
before we go on, I guess I'm still a little confused on how choosing to represent your wave function in Slater determinants is an approximation. Like, what information are you losing by representing it in this way?
Because it's only one single state. So normally what you should do, if I go back, you should, of course, let's forget about 3-body, okay? And let's say we just have 2-body here. You should put in this residual interaction, okay? This should be there, okay? If you put that in, and then you construct states, all possible states here. So you put your particles in the way you have already done with Rick. So basically, where did I put my pen? Right, so basically the ground state will be filling all your particles up to a certain level. So that will be one state. But then you will be other states where you put one particle here. These are all Slater determinants. Okay, so all different Slater determinants. You have, in fact, you have an infinite series if you don't make some kind of an approximation where you said, well, I will cut off the levels at some energy, for instance. Now, so you have a series of Slater determinants, and this will be a basis state. This will be your basis, and in this basis, this interaction, this residual interaction, is not diagonal. So you have to construct your matrix in your Slater determinant basis and diagonalize it. So that is a much more complicated problem than the Hartree-Fock, which, okay, said I will take a basis which is an eigenstate of this Hamiltonian and then calculate the matrix element of the full Hamiltonian in that state. So this is an approximation. Is that clear?
The difference is still really subtle to me, 'cause it seems like we're just building our basis out of Slater determinants, but as long as this basis is complete and orthonormal, we should be able to get the full solution.
Yes, that is true.
So
But that's
like-
very difficult.
Okay.
Because then this basis is infinite, and even as I will show, I think tomorrow or something, and Rick already showed, if you now construct, even if you do a modest truncation, I mean that you say, well, let's consider a few, the valence levels here and put particles there, your basis becomes huge. And so you have an enormous diagonalization problem in front of you.
But to me, that seems like the approximation is drawing a line somewhere. Not, as long as you're using the full infinite basis, it should not be an approximation, right?
That is right. But Hartree-Fock is not at all that. Hartree-Fock is no diagonalization. It's just a Slater determinant, and you minimize the full Hamiltonian in that Slater determinant. If you do a correlated calculation, so if you do construct all your Slater determinants and you do the diagonalization, your ground state will not be a single Slater determinant. It will be a superposition of them, right? And so often what is used is the term correlated wave function, and that refers to the fact that you have a superposition of different Slater determinants. We will not be doing Hartree-Fock, or at least I will not be doing Hartree-Fock, but I will look at the problem of constructing some kind of Slater basis and diagonalizing the Hamiltonian in that. And actually seeing whether there are some simple solutions of that problem. Okay. This is something, this is actually the title of a chapter of Lawson's book, and I sort of like this. He calls it Poorman's Hartree-Fock. Okay, so what is the potential that you would get from Yeah, I'm sorry, Marek. So if you do this, what would be the best, or let's say a realistic mean field that you would obtain would be looking something like this. It has a flat bottom, and then it goes like that. Okay. This was already discussed by Rick, and unfortunately, I mean this. So here you would have potential V1. This is R, and it's spherically symmetric, at least here. And this, of course, this can be solved. The Schrödinger equation associated to this potential can be solved for one particle, and we can construct later determinants, etc. The problem with this is it's not an analytic potential, right? So you cannot solve it analytically. And one potential you can solve analytically is a harmonic oscillator potential, which goes something like that. So this is like proportional to R squared. Okay, and actually there are two potentials, well, two simple potentials which can be solved analytically in 3 dimensions, or well, in n dimensions actually. One is the harmonic oscillator, and the second one is the Coulomb. And well, harmonic oscillator is better suited for nuclear structure than, so you take a harmonic oscillator. Okay. And so where is the poor man? The poor man is, of course, you do not take a mean field potential that comes out of your Hartree-Fock procedure. You take something which is an approximation to it. Okay, let me discuss a little bit because I would like to make some points about adding these guys, but let me first assume that I have a pure harmonic oscillator. This you probably know, but no. R squared. So this is harmonic oscillator, and there is nothing added to it. Okay, and what you probably know is that the eigenfunctions of this guy can be written as n and m. They depend on spherical harmonics, something like that. Right, so they have a radial wave function, which depends on the oscillator, I mean the radial quantum number, so which is related to the number of nodes, and this just depends on R. And then you have spherical harmonics, L, Ml, depend on theta and phi. Okay, so this would be a solution. If you, at the moment, I don't want to discuss spin, right? So this would be the solution for a spinless particle. And so out comes the radial quantum number n, the orbital angular momentum, right? So this is the angular momentum which is associated with, I mean, classically, so the angular momentum vector is R cross P, okay? And so this is the quantum mechanical analog, and then ML is the projection of the angular momentum, the orbital angular momentum on the z-axis, for instance, traditionally. So this is the solution in terms of spherical coordinates. I hope everybody knows what spherical coordinates are. Right, so you have x, y, and z. You have a point here. This is R. You do the projection, right? So this is theta, the angle between the R vector and the z-axis, and then this is phi. Okay, so this is the definition of spherical coordinates. And of course you can also solve this harmonic oscillator in Cartesian coordinates. This we will do in one of the exercises. But it's more convenient to do it in the spherical coordinates because of the spherical symmetry and the definition of the orbital angular momentum. Right? So these wave functions are characterized by good orbital angular momentum immediately. Okay. Now, we have to put in spin. Okay. So how do we do that? So let me use this notation, and I will often just write here R, okay, for all the labels. So now I would like to put in, I forgot it again. Right, I will multiply it. The spin is 1/2, but then it's characterized by the projection of the spin on the z-axis. And this is, I will put a label k in general, and so this is then a spin now which is associated with the particle k. Okay? And so this will be a solution of this harmonic oscillator potential, right? It's independent of the spin, right? So the spin doesn't come in. But if your particle has spin, this would be the proper eigenstate of that Hamiltonian. Okay. Now, this is inconvenient to use. Why? Because it defines the orbital angular momentum, its projection. It defines the spin and its projection, but it doesn't define the total angular momentum, and we will see in a moment it's nice to have the total angular momentum. So if you look at the properties of the operator L squared acting on this wave function, it will give LL plus 1 times this wave function. That's let me forget about the k indices. This is for a given particle. Okay, similarly, if I act, well, I should put here, if I put the units h bar omega squared, right? Act with Lz on this state, what is the eigenvalue is just ml h bar. Same thing for s squared. Right. It will be 3/4 h bar square, and finally sz is ms h bar. Okay, so this is possible. This is a basis of your Hamiltonian for a particle with spin, but it's much more convenient to use a basis of this type. L S, so which is 1/2 J and J. And how do you define it? It's just a superposition of Clebsch-Gordan coefficients, so L ML 1/2 MS to J MJ. Okay, the summation is over the projection of the orbital angular momentum and the spin, and here you have your original. Yes, and actually I forgot here to put. Okay. So this is just a unitary transformation from one basis to another basis, and these are the famous Clebsch-Gordan coefficients. And so they are here used for the case of coupling orbital angular momentum with spin 1/2, but they can be used for any angular momentum, system J1, with angular momentum of a system J2 to a total angular momentum J. Okay? And the nice thing of this is that now you have, let me erase this. If I now put in here my wave functions in this, what are the properties? So L squared is still defined, so it's L plus 1 h bar squared. Okay. Lz is not defined, so there is no eigenvalue associated with the projection of Lz. Why? Because you have a summation here over ml, so there are different ml values coming in. So, but what is defined is s squared, right, which is 3/4 h bar. Then we have j squared, which is jj plus 1 right, and jz, the projection, which is mj h bar. Okay. And this is much more useful as a basis because it defines the total angular momentum and the projection of the total angular momentum. This is for one particle, but you can do the same scheme for any set of particles that arrives, that you consider. Okay, why do I say that? Because you see here, this guy here, so how can you deal with that? That's now rather easy to do. Because you have j, the vector j, is the angular momentum vector is L plus the spin. So j squared is this squared, and so L dot S, right, is 1/2 j squared minus L squared minus S squared. Yes, I will not use consistently hats over operators. Okay, so it's a little tedious, but you understand what I mean. So this, which is written there, L dot S, is a combination of j squared, L squared, and S squared. And so now you see why it is convenient to use this basis, because you have a basis where j squared is diagonal, L squared is diagonal, S squared is diagonal. So this is the appropriate basis for considering the spin orbit term. And the same thing, of course, for the L squared, of which the eigenvalue is just LL plus 1, h bar squared. Okay, so this, I'm sure many of you will know this, but it's just to introduce the notion of Clebsch-Gordon coefficients, and it's also to show that if you go from one basis to another, right, this, of course, physically, because this is a unitary transformation, so you could do your calculations in this basis or in the other basis, you would obtain the same result. But a change of basis might be easier to interpret results. Right? So that's the thing to notice. This is a unitary transformation, and we will see later that if, for instance, if you do transformations that are not unitary, and then things become a little bit more complicated. Okay, so this is a repeat of what Rick already showed and what I've here indicated. So you have eigenvalues which are now, so if you introduce this orbit-orbit term, right, then you have an extra term LL plus 1 and the spin orbit. So this you can work out from this expression here. So it's minus 1/2 of L if the spin and the orbital angular momentum are aligned, and so it is plus 1/2 L plus 1 if they are anti-aligned. And so this is just nomenclature. I call here N the oscillator quantum number. It goes from 0, 1, 2, etc. This is the radial quantum number. There are different conventions. This you have to be a bit careful about. Sometimes it starts from 0, right? Sometimes it starts from 1. Okay, this is a convention. Here, if it starts from 1, the relation between the oscillator quantum number, the radial quantum number, is like this. Okay. This is the orbital angular momentum, and then, of course, the total angular momentum is L plus or minus 1/2. This is, well, I don't need to go into that because you had a long discussion, many exercises about this. And so this is the traditional, let's say, level energy spacings if you put in the standard spin orbit values for the spin orbit interaction and the orbit-orbit interactions. And this leads to the magic numbers, at least close to stability, which are listed here. I never liked actually this word magic because, okay, I mean, it sounds like magic, yes, so which is not what you're doing here, but okay, so Rick discussed why is there an orbit-orbit term. This is essentially the same argument. It's put in a little bit of a different way. You see here, this is the harmonic, this is a figure taken from Bohr-Mottelson, so this is the harmonic oscillator potential. This is a Woods-Saxon potential, which is closer to reality. And you see that there is, on average, I mean, the energy would be the same, but now if particles are driven to the outside of the nucleus, then you see that the oscillator potential is less attractive than the Woods-Saxon. And so if you have an S state, which is spread over the whole nucleus, then this difference doesn't matter. But if you have, and this is the case of a G state, so a high orbital angular momentum state, then the wave function is peaked at the surface, and so in first order perturbation at least, so the energy in a Woods-Saxon would be lower than it would be in a harmonic oscillator. So this is a simple example why you have to put in this orbit, a simple argument why you have to put in this orbit term. The spin orbit term, we had already a discussion. I don't have I usually think of it has a relativistic origin, so it comes from the Dirac equation. Right, there is something which, this is also is difficult to understand, but there is a general symmetry argument that actually, yes, what I showed here, I put it here as I should go to the original, as constants, zeta, and a constant kappa. Actually, these are not constants. They may depend, and they do depend on r, on the r coordinate, so the distance from the center of the nucleus. And so there is an argument, sort of a basic argument, which is difficult for me to understand, that this function should be proportional to the gradient of the potential. So this should be proportional to dV/dr, right? It turns out that if you do this for a harmonic oscillator, this is a constant. So, yeah. Okay. Yes, I want to do one more thing about the independent particle model, and this is some empirical evidence for shell structure. Right? Rick gave several examples. Basically, if I remember correctly, if I paid attention, it was separation energies and the excitation energy of the first two plus. Okay, and BE2s. Sorry, I didn't pay. Okay, so I will show one example which I sort of like, where you just take it also from masses, right? And the only thing you use is the liquid drop mass formula. This is, I guess you're all familiar with that. So this is a sort of an expression for the binding energy of a nucleus. So I call it here B. It's a function of n, the number of neutrons, and z, the number of protons. And then A is, of course, the sum, n plus z, right? And this is a simple expression which is known as the, sometimes known as the Weizsäcker formula, right? So it has a volume term, a surface term, it has a Coulomb term, and then this is a symmetry term. Okay, and then this pairing, but this is a correction which is not so important here. Volume, this was discussed by Rick. So because of the nature of the nucleon-nucleon interaction, the binding energy doesn't scale with A squared, it just scales with A, okay? Because nucleons interact only with the surrounding nucleons, not with everybody in the nucleus, right? There is a surface correction because the nucleus at the surface, they can only correct, they don't interact with as many nucleons as one the inside. There is obviously a Coulomb correction, right, because you have a Coulomb interaction between the protons. And then this is some kind of a quantum mechanical effect. This comes from the Pauli principle. You cannot put nucleons in the same quantum mechanical states, and that is why they prefer to be different, right, because then they can minimize their energy. So if it would be for this term, the stability line would be at n equals z, and so this stability line is shifted because you have protons. So the stability line is actually completely determined by the ratio of those two effects. Coulomb versus symmetry. Okay. So you can now do, well, I did this a long time ago, so I didn't go take the new mass data. Right, these are the coefficients you find. And this is, as it says, it's a liquid drop mass formula. Right? It has this quantum mechanical effect, but it doesn't know about the shell structure of a nucleus. Okay, so it ignores shell structure. So then you might say, well, let's compare this with masses. Here I plot so the masses which I took from the, yeah, no, this one. Okay, so which I took from the 2003 compilation, and so you see these are binding energies. Actually, I should put binding energy surface, right? So, and you see this is oxygen 16, right? And then it goes up to 2 GeV. So that is the maximum binding energy for a very heavy nucleus. Okay, and it's a very smooth surface, right? So the binding energy goes up. You don't learn much about it, right? And what you have to do now is what you could call unfolding. So what you will do now is to say, well, let's take the experimental and let's subtract from it the liquid drop mass formula. And so this is what you get. And so you immediately get the shell structure becomes immediately obvious. And well, for light nuclei, it's not so clear. You have to zoom in But let's just look at the heavy nuclei. So this is tin 100, 50-50. This is tin 132. This is lead 208. And you see, this has nothing to do with stability. It doesn't say that tin 100 is stable. It just says that if you look at the binding energy of tin 100 and you compare it with what you got, you would obtain with the liquid drop model, tin 100 is much more bound than predicted by the liquid drop model. And so the difference between the two is related to shell structure, is the increased stability of nuclei when they are in a closed shell configuration. Okay. Is that fine? Are there any questions about this? Or okay. What is the... Okay. So now, what I would like to do now, let me a second. Oh. Is to discuss in detail two nucleon configurations. So this is a little bit a repeat of what Rick has discussed, and you had exercises about that. But these exercises and this discussion was always in the M scheme. So now I will do the same problem, but now I would like to do it in a coupled basis, right? And I will do two examples. One which is not so difficult. So this is coupling of, or the construction of two nucleon states. And the second one, which is, I think, difficult, and so there I will take my time. That is the construction of three nucleon states. And then at the end I will do the generalization to n nucleon states. Okay, so this is the plan. So this two nucleon states, many of the things that were found in the uncoupled basis, I will find again here, but from a different perspective. But it's always interesting to look at problems from different perspectives. I think this is something, yes, when I was young, I didn't do that enough. So I found the solution of a problem and I said, that's it. Instead of saying, yes, but what does it mean? Can I look at this problem from a different perspective? If you do that, you always learn, you understand better what is the nature of your solution. So that is what we will do now for two nucleon states and how they can be constructed in a coupled basis. Right?
Steve,
Yes?
could I just make a quick comment? Just to avoid any confusion, he uses phi and psi the way he's defined it. In the first day, I also used phi and psi in two-state mixing to mean the unperturbed states and the perturbed
yes.
states. Don't be confused by that. We're using them in two different ways.
Yes. So as I said, the phi here, it refers to the antisymmetry character of the phi and the xi. The phi and the psi. Sorry. Okay, so yeah, this is actually a summary, so maybe I just go out. This I will do slowly, because So this is an uncoupled state. This is a state as you have encountered it in the exercises, where you look, well, in the exercises, the J1 was always equal to the J2, right? They were sitting in the same orbit, but you were distinguishing the, or counting the magnetic substates. Okay, so now what I would like to do instead is to consider yes, I have to make sure my notation. Yes, let me follow the notation that I put here. Yes, right, J1, J2, Xi2, and then I couple to Jm. This is again with the Clebsch-Gordon coefficient, so it's a sum of M1, M2, J1, M1, J2, 2. Okay, so this is the coupled state, right? It doesn't say anything about antisymmetry. So let's now define an operator. P12, right, which interchanges these two guys. Okay. It interchanges all the coordinates associated with particle 1 with the coordinates associated with particle 2. So this is easy to do here. I just switch the indices 1 and 2. Okay? Fine. Now I'm going to do a little trick. Well, I don't have to rewrite it. Maybe you will have to rewrite it, but I can erase it. And I will switch the indices J2 and M2 here. Right. This introduces a phase, and the phase is known for a Clebsch-Gordon coefficient is J1 plus J2 minus J. Okay. And so then these are just C numbers, okay, so I can just switch them around. I now have proven that this is minus J1 plus J2 minus J, and then this is phi J2 Suppose now that J1 equals J2 equals J. This is the case you did a lot yesterday. So what is the effect? So P12, the interchange of 2 on a wave function which has this structure. Is equal to minus 2J plus, well, minus, but it doesn't matter. Yes, I got that right. Okay, and this is for a fermion. We're talking about fermions here. J is half odd integer. Okay, so this is, I can replace it by minus 1 to the power j. And of course we want a wave function which is antisymmetric, so that implies that j must be even. So we find back the same result that we found from the M scheme. Okay, you can do this analysis for bosons. Okay, so you have two angular momenta. It's the same kind of derivation. You find the same factor, namely 2j minus, and so in here 2j minus j. Okay, the j is integer, so minus 1 to the minus j is the same as minus 1 to the power j. That's the same. Okay, but then of course you want your for bosons you will not have this minus sign here, but then you want to have your wave function which is symmetric for bosons, and so again you find that for bosons the j must be even. Okay, so we find back in the coupled basis the same rule that we were that we encountered in the M scheme. Then you might say, well, but what is the advantage? Well, let's suppose now let's put in isospin. So let's put in isospin. Okay, so now I will consider a wave function which is characterized not only by the coupling. Well, I should put also isospin labels, but I won't do that. And let me put it for j equals j1 equals j2. Right. I couple this to j, total angular momentum, its projection mj, and I do the same thing for isospin. Okay, I have two particles, they have isospin 1/2, so the t can be 0 or 1. Okay, the coupling of two 1/2 angular momenta. Let's now do the same argument. I apply my permutation operator. This guy, so I will interchange all the coordinates associated with particle 1 with all the coordinates of particle 2. So now maybe I should just write explicitly because this is sometimes, let's call it m and m prime. So j m prime, j m. Okay. The same thing you have to do for isospin. So it's 1/2 for one particle projection mt, 1/2 for the other particle mt, and then coupled to total isospin. Okay, and so this will be written in terms of the uncoupled well, I should put here now explicitly this is particle 1 and this is particle 2. Okay, so this is the equivalent, but now written of this kind of expansion, but now it is done, the coupling in spin in angular momentum, I should say, angular momentum, and in isospin. Then you go to the same argument, you do these switches, you use the symmetry properties of the Clebsch-Gordon coefficients, and so what you will find is that you have that this is J plus T So the rule is, if we're dealing with fermions, the rule is J plus T must be odd. I want to construct a wave function which is completely antisymmetric, so I find the rule J plus T must be odd. Of course, if T equals 1, if we have two identical nucleons, that means that J must be even, right? So, of course, I find back the result that I derived here. But now I can say if I couple two nucleons, whatever they are, okay, two nucleons, the sequence of JTs that are in the same orbit, the sequence of JTs that are allowed is 0, 1, plus 1, 0, plus 2, 1, plus and so on. And the maximum, of course, the maximum angular momentum is 2J, right? And then if I have this, of course, this is an odd angular momentum, then the T must be 0. Okay, so you see that in the beginning this might say, well, I just find the same result as I did in the M scheme, but then it's powerful because you can put in a simple way the consideration of isospin. So now we know the rule. What are the spins and the isospins we can obtain for two nucleons? Two nucleons in general, neutrons, protons, neutron-proton system. Okay, so this, what is, yeah, I think, yes, this, I think it's a good time to have a pause. This is a summary, huh? Yeah. So this is a summary. It's essentially what I wrote here. You can write it in a little bit different way. So this is just picking out the positive J's. Okay, I would like. I think I will have a break here because what I will do after the coffee break is to do this problem for 3 particles. And this is, you will be confused and amazed, and this is a difficult problem. But don't worry about it, there will be exercises on it. Well, maybe you should worry about it then. But hopefully these exercises, they will sort of give you a better understanding of this has to do with this famous or infamous coefficients of fractional particles. So back in half an hour. Yes?
Can I just ask one question? You, we have 1 minute.
Yes, yes. No,
You referred to the one-body potential.
yeah,
You also referred to the idea of mean field.
yeah.
What do you mean differently by the two?
Yeah, the kinetic energy, of course, is it's included in the one-body term, right, of the independent particle shell model.
And by mean field?
I'm not sure. The one-body potential refers to the potential, okay? Mean field, I would say it includes all one-body, including the kinetic. But it's a semantic...
I ask because a lot of people are confused.
yes. But in the one-body term, of course, includes the kinetic energy. And it's very important because in many ways the two contributions are cancelling each other. Okay, are there any other questions? Well, if not, then we have a break.
You said what I meant to say.
No, you said it better.
I want to ask full Hamilton
Yeah.
again. This you said this sum as a of 2 and 3 body fun. This part include 4 body or 5 body
Yes.
as a unknown contribution.
Yes,
But this is should very small.
yes,
Uh-huh.
hopefully.
Yes, hopefully. Yeah. And when we calculate Hartree-Fock, you said this Hamiltonian is full Hamiltonian.
Yes, yeah.
So this include 3 body or
In
4?
principle, yes. I don't know whether they actually do it
Yeah.
because it's three-body calculation, but it's just one Slater determinant, so that is not so hard.
Yes. Usually